the recording. Perfect. Okay, good morning, everyone. A second episode of C for C++ for C programmers. Actually, this one could probably be beneficial to a number of already C++ programmers, because I'm going to focus on modern C++ features. So I mentioned last time, okay, I hope everyone is in the Slack channel. That's my preferred location for posting questions and code snippets. If you have a piece of code you want to show or questions, triple backtick and then cut and paste. So I hope everyone is in the Slack channel. The Slack channel also has the Zoom link. It has the textbook download and the lecture slides download. And the lecture slides have been updated since last week for today's topics. So please download the latest, which is what I'll be presenting from. Okay, time to share a screen and let me just, I think I'll just only support only mirror the slides. I'm going to give one or two programming assignments, so if you feel like doing those, make sure you have a C++ compiler somewhere handy. Okay, last time we did mostly object-oriented programming and vectors. So don't use arrays, use vectors, and instead of passing your data into functions, see if you can capture stuff as much as possible through object-oriented programming. Okay, so those are the two big improvements of C++ over C. But there is a whole bunch of other things, and that's what we'll get to today. So, for instance, in scientific computing, string handling is not the most important topic, but so we typically don't worry about buffer overflows and security problems because of string handling, but string handling in C++ is a lot better than in C, and I'll very quickly go over that. So this must start to look familiar. You include a header string and then you say using standard string. And now all of a sudden the keyword string has a meaning. So no longer malloc, char star and that sort of stuff, right? Absolutely no need for it. So you declare a string, which is then a zero-size array of characters. There are various ways of initializing it. So initializing with curly brackets, parentheses. Unfortunately, initialization in C++ is not the most elegant thing, and there are some subtle differences between doing it the one way and another. And you can assign to a string. So strings are delimited by quotes. So string 1, I'm using parentheses for initializing it, and then the double quotes enclose the string. On line 3, there are escaped double quotes in the string, and if you have a really weird string, then there is a syntax with a capital R. I think it stands for raw string, and so you enclose R double quotes, and in between that you can have anything you want. So various ways of creating strings. The big advantage of C++ strings is, of course, like that they have the dynamic behavior like vectors. So you could extend a vector by push back something, and likewise you can do addition on strings. Makes life a lot easier than doing all the mallocing, reallocating in C. Just like vectors, strings have a size method to ask how long are they, and you can index them with both the square brackets and the add method. As with vectors, you can range over a string, so if you need to investigate the individual characters, you can range over it, use ranging or use indexing. Ranging with reference. I hope everyone still remembers this from last week, that I don't have to explain the meaning of this. If you do, I don't mind if you unmute for a question or post in Slack. And we'll get into this sort of iterator mechanism later. Let's see, strings. Yeah, some of these exercises are for my full semester course, so do them yourself if you want to make sure that you understand things. Okay. Strings and output are special cases of more general mechanisms. For instance, there is something called a string stream. And in the code example here on line 4, you recognize what we've been doing last week. Cout means output to the console, and then double chevrons to pipe stuff to output. David, I don't think there is any difference apart from really subtle stuff. Yeah, I don't want to go into that, but I think they're basically equivalent. The compiler understands both of them and translates them to the same mechanism. So in this code snippet on line 4, you see regular output to Cout. On line 3, the double chevrons are also used, but there the string and the values are not going into output, they go into string stream. So console output is a special case of stream. And a string stream is another stream. And so if you pipe stuff into a string stream, it goes into this object, and then later you can take that object. So this is kind of cool. You can build up a string by adding stuff to that stream and then outputting it to Cout or to a file or something. So string stream. String stream can usefully be used for the following. Let's say you have a complicated object and you want to be able to display that on Cout. So you could do that by having a method in your class as string. So object.asString gives you a string representing that object, and you do that by creating a string stream. So for instance, this object is a XY coordinate, and so if you render that object as a string, you want parentheses x comma y parentheses, and so you make that string stream. You pipe the paren x comma y paren into the string stream, and then you return the string stream, the internal string of that thing. So now you have your object as a string. Okay, line 7 through 10 is absolute magic, and just remember that it's in this course and you can copy it later. I mentioned briefly last week that you could overload operators. So what this bit does is that it overloads the less operator so that you can not only render numbers and strings and to output, but now you can also render your line 8 at the end. You see point P, so you're rendering a point object. So now you've overloaded the less operator so that it can work on any sort of output stream. Okay, you don't have to understand this. Just remember that it's possible to apply cout and that sort of thing to objects with a little trickery. Okay, so right, so this illustrates the previous slide. You have a point, and then you do cout, and at the end of line 2 it says P1. So normally you cannot cout, you cannot printf struct. Right, in C, it's the same thing. You cannot printf struct. Likewise, in C++, you cannot cout an object. And with the trickery on the previous slide, it now works. Let's see. Okay, so that was about strings. There's a whole lot more sophistication to strings. In certain types of applications, people worry about that a lot more than I do, so I'm leaving it at this. I/O. So mostly I'm going to say something about terminal I/O and a little bit about file I/O. If you're used to C, then I'm sure you know all the options to printf and things like scanf. In C++, unfortunately, there are two mechanisms. So you can use the old C stuff, of course. Then you can use the cout that I have been using in examples. But yeah, you may find this sort of stuff a little tedious to write. See line 3. Isn't there an easier way to write parentheses value parentheses close? And so, yes, there is a new mechanism. So the cout mechanism exists, but someone wrote an open source library called FormatLib. And as of C++20, it has been rolled into the standard. Actually, this slide is a little behind the times because I think most compilers these days do support it. So FormatLib is part of C++20. And what is the difference? Okay, so I'm going to show a number of examples of how to format simple output. So here is cout successive powers of 10. So now, for instance, make that right aligned or use a fixed number of positions, and how to do that in C++. Okay, here's how to if your compiler does not support standard formats, then here's how to get FormatLib. Let me just show a number of examples. So, for instance, if you print out a column of numbers, you may want them right aligned so that the units and the tens are aligned. So see the output. So in the output, I'm using 6 positions, and if it overflows 6 positions, then yeah, overflow to the right. So how do you do that? Okay, you need a new header, IO manip for manipulation, and then you use the keyword setW for set width. And now on line 6 and 7, I say number and then set width 6 for the following number. Okay, and that gives you the output on the right. And this is very easy to use. And I find that right aligning a column of numbers and giving it a fixed number of positions is by far the most common thing that I do in ASCII output. In format lib, instead of cout, you use format print, or if your compiler supports this, then it's standard print. And if you are used to Python and you're using F strings in Python, which is 3.89 or thereabouts, I don't know when this was introduced, then this may look familiar to you. So you have your format string between double quotes, and anything between curly braces means print the value of something. So in particular, there's one curly brace and it gets resolved with the variable I, and then it says right align 6 positions. Okay, you can sort of see the logic of this. Now, this format lib can do a whole bunch of customization, and I kind of find it hard to remember what all it can do. So yeah, I have a cheat sheet somewhere. So the next thing you may want to do is not just write a line, but use a padding character in the standard IO stream and IO manip. That is the set fill routine, and so you declare a fill character, gives you the output as on the right. You can also do left aligning in format lib. Yeah, so 0 colon dot, what was that on? Yeah, I'm not even sure that I know what that 0 means. Yeah, so the format print, standard print has a whole bunch of options on how to format stuff. So find a good cheat sheet somewhere, and then it'll become second nature to you at some point. Different number bases, fixed point formatting, scientific notation formatting, it's all possible. So I'm just mentioning this. There's no point in me going into a lot of detail. So in the example so far, you did include IO stream to get stream to your console. You can also have an F stream, which instead of to the terminal goes to a file, and then instead of doing cout, you now declare an OF stream, an output file stream, which you open, and then you can pipe with less anything to your output file stream the way you would normally do to console output. Okay, and quite painless, works very nicely. All right, this slide is sort of duplicate, so yeah, it's about redefining the less operator so that you can output your own objects. Okay, today I want to get mostly to 3 big topics: smart pointers, lambda expressions, and then 2 smaller topics, all sorts of union-like things, and iterators, in particular iterators. So smart pointers, lambdas, iterators. Okay, smart pointers. What are smart pointers? They take the place of C pointers, and C pointers really are not pointers, they are addresses. And C++ is a lot more explicit about abstraction mechanisms, and so your C pointer mechanism is barely needed. You don't have to do character arrays, you have strings. You don't have to malloc so many size of floats because you have a vector of floats. Parameter passing by reference now goes with actual references, what I did exactly a week ago. And the only thing you need pointers for is ownership of stuff and ownership that transcends scope. So smart pointers have a very limited applicability in many applications. Linked lists and graphs are the prime example that I usually use when I'm teaching. So I will use linked list as a running example here, although C++ has its own linked list class built in. So don't write your own linked list. I'm just using it as an illustration of pointer mechanisms. Okay. What is the point of smart pointers? Memory management. With C pointers, it is much too easy to have memory leaks. And so smart pointers solve the whole thing. In fact, you shouldn't call them smart pointers, although that is the usual terminology. It is really a smartly pointed object. So it's not so much that you have a pointer to an object, it's that you have an object with a pointer to it, and the object keeps track of how many pointers there are to it. And so when no one is pointing at the object anymore, it deallocates itself. I will illustrate this, but this is the key to never having memory leaks anymore. Okay, is someone going to type in Slack the standard counter example to this argument? No one? Circular lists, they can be self-referential and no one points at them, and yet you cannot deallocate them trivially. Okay, smart pointers. So smart pointers only work with objects. That is the main reason for their existing. You create an object with a smart pointer to it. It is not necessary to have a smart pointer to an int. Doesn't make sense. Okay, so we make a class. It has one member, a double X, and so I call my class has X. You create it, and there is a get and a set routine. That's not how you code things in practice, but just for purposes of illustration. So I have an object, and I can put something in it, and I can ask what is in you. So instead of now creating an object, you create the object with a smart pointer to it. And for that, you use the make shared routine. So instead of calling your constructor has X with parenthesized the constructor arguments, now you say make shared has X, and you give it the constructor arguments. Note that I'm using auto. I could also spell it out. Shared pointer to has X. X is make shared has a. Yeah. Okay, this is halfway redundant, so I'm just abbreviating this by using the auto keyword. Now compare how you would use an object versus how you use a smart pointer to an object. Did I mention that the smart objects come out of the memory header? Okay, line 1, yeah? Okay, on line 5, I create an object, and then on the next 3 lines, I do this object dot value dot set, yeah? So use the dot notation for methods of the object. You've seen this last week. If you have a shared pointer, then it starts looking with like the syntax that you're used to from C. Instead of the dot, now you have the arrow notation. So So my X pointer is a pointer to a hasX, and anything that is available to me in a hasX object is now available in the hasX pointer by using the pointer dereferencing arrow. So arrow value, arrow set, and it does exactly the same thing. Right, the memory header, and then you use the routines like shared pointer and make shared. And I will very briefly say something about unique pointers. So I'm just mentioning that they exist. A lot of people say you should never use shared pointers, always unique pointers, but I'm not entirely convinced. And shared pointers are definitely easier to teach. So I'm teaching you shared pointers, and then convince yourself that you may or may not have an efficiency argument for using unique pointers. Okay. So a shared pointer is an object plus a reference counter. And if you, for whatever reason, need the actual object, then you can take your shared pointer, and .get gets you the C style pointer to the underlying object, and then you can star dereference it. I'm mentioning this in case you run into a borderline case where you need to undress a smart pointer and get hold of the actual object. Like I said, smart pointers belong with objects. You cannot take things like scalars and make a C-style pointer smart. Doesn't work. Exercise. Okay, the whole point was memory management. Well, no. The big advantage of smart pointers is memory management. So I hope everyone knows what a memory leak is. In this code example, I have a scope with curly brackets, and before the scope, the variable array doesn't exist. And then in the curly brackets, for instance, a function or something, I create an array, I do something with it, and then I forget to reallocate, to free it. So after the scope, the variable doesn't exist anymore, but the memory is still there, and no one is pointing at it, so you've lost that memory, and that's called a memory leak. If you do this in a loop, then of course you will in the end fill up all your memory with useless crap. Languages like Java and Python solve this through garbage collection, meaning that every once in a while your program will hiccup, and because it needs to collect all the crap that's in memory. And yeah, hiccups are fine if you're a web server. They're not fine if you're running a game engine and you want to shoot your enemy and suddenly you hiccup for a quarter of a second. That is more than human reaction time, so you don't want that. So that's why game engines are written in C++. The Webb Space Telescope is written in C++. Just mentioning it. Okay, so yeah, smart pointers are a great way of not having memory leaks and having an efficient mechanism for not having them. Okay, let me illustrate this. So what I need is a class that reports when it's created and when it's constructed and when it's destructed. Okay, so my class thing, I have a constructor that says I am being constructed, and then the destructor is that thing with a tilde. I said last week that you almost never needed, and indeed I'm just creating it here to print out something. So normally there is a default one that gets called invisible to you, but here I'm making it visible because I want to know when it's being called. Okay, so constructor, destructor, now they report when they are in action. Okay, so line 1, I report that I'm outside the scope and print that. On line 3, I'm creating a thing object inside the scope. So it says calling constructor. On line 4, I print that creation has been done. And then on line 5, we leave the scope. And so the name X disappears. It's no longer in scope. But the magic of C++ objects is that the object gets deallocated. So in the output, you see calling destructor, and that is not triggered by anything you do as a programmer. It's done automatically when the object goes out of scope. Interesting typo on line 6. Okay, so this was not about pointers. This is ordinary C++ behavior, and this stuff has a fancy name, which I'm not going to tell you because it's completely uninsightful. And I don't teach this stuff because it does basically what a language is supposed to do. It's only silly C which has the memory leak problem. It doesn't deallocate automatically. Okay, so now we have this class that says I'm being constructed, I'm being destructed, and we're going to combine this with smart pointers. So set pointer 1, okay, I create thing pointer 1 as a shared pointer to a thing. And then I say I'm going to overwrite the pointer, and I do that by setting null pointer on that thing. Okay, in C, this would have been a memory leak because the thing object is never freed, but the pointer to it is overwritten. And you see in the output that there is a line that says calling destructor. So when you overwrite the pointer, the object says, okay, no one is pointing to me anymore. And so I'm deallocating myself. Okay, that's the solution to the memory leak problem with pointers. To do a slightly more sophisticated problem example, I create a thing pointer 2 as a shared pointer, and then thing pointer 3 gets copied from thing pointer 2. So now you have 2 pointers to the same object. On line 9, I am overwriting pointer 2. So that one points to nothing anymore, and only pointer 3 still points to my object. And so if you look at the output, it says overwrite pointer 2 and nothing happens. It's only when you overwrite pointer 3 and no one points at the object anymore that the destructor of the object gets called. Okay, so this is called reference counting. The object counts how many pointers there are to it, and if there are no more pointers to it, then the object destructs itself. Okay, wonderful mechanism. Let's see it in action briefly. Linked lists. So I'm assuming that since I'm talking to well-versed C programmers, that everyone knows what a linked list is. Okay, so you need a class list, which is maybe a pointer to the first element, and then every element is a node object that potentially points to another node object. So how do you do this? A list is a shared pointer to the head element, and you initialize that with a null pointer. So if the head pointer is null, then the list is empty. The node class, let's say that a node has an information field of data, and it's maybe a count field, how many times that thing appears, multiplicity. And then the node has a shared pointer to the next node, and initially you set that to null. Let's see. So the constructor for this the node class, take a look. There is a default constructor, which may or may not be necessary, and there is the main constructor, which says make a node with a certain value. And it does that, and then the next on the next line, you see the member initializer list. So value gets copied into data value, data count gets set to 1, and the next member gets set to what? The argument next. What is this equal sign here in the constructor? Post in Slack if you know the answer. I discussed that last week. David, correct. That's a default value of the argument. So that means if you don't supply that argument, then it acts as if the default value was there as an argument. Okay, it is easy enough. No, wait a minute. I'm going to show you examples of how to use, how to compute the length of a list. And yeah, so if you take my semester course, then you get as a homework, write an insert routine. But I'm assuming that the audience here has already done that somewhere in their past. So I'm mostly showing a couple of mechanisms. So the list class head only has a head member, and so if you print a list, then if there actually is a list, then you print from the head, and then you print a new line to to round it off. How do you so the head is a node, and so you also need a print method in the node class, and that's on the right side of the screen. So how do you print a node? You print the data value and the count, and then if there is a next node, you print that one. Okay, this looks exactly the same as it would have been in C with the arrow notation. In fact, none of this stuff has the shared pointer appearing anywhere in it. Okay, this should also be trivial. How do you compute the length of a list? Well, if there is no list, then it's 0. Otherwise, it's the length of the head. And what is the length of a node? That is 1 if there is no next, and otherwise it's 1 plus. Right? Simple recursive programming. I hope this is not a problem to anyone. This is exactly the same as you used to do in Algorithms Data Structures 101 whenever you went to college. Okay, yeah, if you have a really long list, then you may worry that you get Stack Overflow by writing something as recursive as this. So maybe, maybe you think your compiler will resolve the tail recursion, and maybe you don't trust the compiler and you decide to write it iteratively anyway. So how do you compute the length of a list iteratively? You do that by having a pointer that goes down the list. And so your current node is initially the head. And if the current node has a next, this is not entirely correct. It doesn't work if the head is, if the list is empty. Let me take a look at that. If I teach this in class, I do a sort of test-driven development and give the students a number of test cases. David, yes, if the list is empty, then head is null, but then the while statement fails. You cannot ask has next on a null pointer. That's my problem here. So yeah, anyway, so I give my students a number of increasingly complicated test cases that they have to go through. Test-driven development. That's actually fairly nice. I'll say something about that at the end of today. Okay, yeah, so then if there is a next, you add one to the count and you go to the next. That is a good question. I wonder if deallocating the head node would cause a recursive. I think that would recursively free the whole thing. So you probably get a Stack Overflow behavior. If you would nullify the head pointer, then what it points to wants to deallocate itself, but it does that by first deallocating what it points to, which deallocates itself by deallocating what it points to. So you still get the Stack Overflow behavior. Okay, so yeah, the question stands: can you do an iterative deallocate of the list? It's not entirely simple, but I'm talking to a sophisticated audience. I'm sure you can imagine how it goes. Okay, so all of this was using shared pointers, and some people say use unique pointers when possible. Okay, what is a unique pointer? It's a pointer that is just as smart as the shared pointer, but an object can have only one pointer to it. So that means that the object doesn't have to count how many pointers there are to it. It is either there is a pointer or not, and then you deallocate yourself. So in a linked list, you can in fact use a unique pointer because a node is only owned by one other node. There's never two nodes owning one node. If you have a doubly linked list, how would you do that? Well, okay, I don't want to go into that. So one problem with unique pointers is that you cannot copy it. If you'd copy it, you'd have two pointers to the same object. And so there is a mechanism for moving the pointer, and that is complicated and tricky, and I'm not going to go into it. I just want to mention that if you use unique pointers, this works. The node class, everything is exactly the same, except that it says unique pointer instead of shared pointer. The insert routine all works fine, except that now you cannot go down the list. So the problem with going down the list is that you had your head pointer, which is presumably a shared pointer to the head, and then you make a copy of it into the current node. So this is a copy of a pointer. That doesn't work with unique pointers. And so if you use unique pointers, then you actually need old style C pointers to walk down the list. And this is where you, for instance, use your get method to get the C style pointer to the smartly pointed object. If you try to write this the way you wrote the other one, the compiler will say, okay, you cannot copy a unique pointer. And okay, what are smart pointers for? They are for if you need to own an object and the ownership transcends scope. So a node gets created somewhere, but then it needs to stick around outside the context where it was created. You can still use C-style bare pointers, but only for this sort of non-owning purposes. And so smart pointers are if you need to own an object, and I use shared pointers throughout, and there is an efficiency argument for if a node is only owned by one pointer, then use unique pointers. Where would you legitimately use smart shared pointers? Well, for instance, if you have a DAG where a node has two parents and none of them is intrinsically more owning than the other. Okay, subtle points. Basically, remember how you create a shared pointer and remember that it solves the memory leak problem. So no more C-style star pointers. Almost never needed anymore. Okay, major topic, lambdas. Lambda expressions, sometimes called closures. What are lambda expressions? They don't exist in C. If you write Python, you may have seen them. For instance, if you use the Python sort routine from the standard library, you can supply your own comparison operator. So if you want to do a sort on objects that you write yourself, you need to write your own comparison operator. When is one object less than another object? And in Python, you can do that by supplying a lambda. C++ has lambdas, and they are useful for things like sorting, where you need a custom comparison, but they have many other uses. Okay, so in cases like having a custom sort operator, you need a small function that is sometimes less than a line long. And so in C, you would have to explicitly define it and then pass its name. That's tedious. It would be so much more convenient if you could just put the function recipe in place. Another purpose is that maybe you sometimes want to define a function dynamically based on a context. So for instance, you read a number from user input, and now you want to have a multiply function that multiplies by that number. And the multiply function should take one number and return one number. Okay, so you somehow want to define that function with the multiplier built in. That is completely not possible in C. You cannot global variables, but please don't, never global variables. So in C, you cannot dynamically define a function. That's another reason for using lambdas. Okay, what is a lambda? Okay, take a look at ordinarily you would say double sum of x and y is return x plus y, and then you can apply the named summed two arguments. With lambda expressions, you take this input parameter specification, the output type specification, and the recipe and write that in one explicit recipe without a name, and you apply it directly. So square brackets, we'll get to that. That basically says this is a lambda, and then two floats as input, trailing output type declaration, out of it comes a float, and then between curly brackets, the same function body. And then you apply it directly to the two arguments. Okay, this looks pointless, right? You might as well write it out, but just to illustrate that square brackets, parameters, recipe is a function, and so you can apply it directly to arguments. So you've seen the lambda syntax: square brackets with something called a capture that we'll get to, and then it looks like a traditional function, input arguments, output type declaration, and then the definition. In cases like here, where you take two floats and you return their sum, the compiler can figure out what the output type is. So this arrow type stuff is actually optional in cases where the compiler can figure it out. That's a lambda expression. So you can apply it directly, and there is actually a use for that. Suppose you have two completely different constructors. The code on the left, if some condition, you want to construct your object like this, otherwise, oh, line 4, the y should be an x, sorry. Line 4, my class y should be x. So the point of the left thing is that you want to construct x in two completely different ways. That code doesn't work. Why doesn't it work? Answers in Slack. Anyway, so on the right, you do that by saying my class x is, and then we'll get to the square bracket foo in a minute. So you write your lambda expression and it calls the right constructor and then returns that object. So there are certain boundary cases where direct invocation is needed. Why doesn't the left one work? No one? The true and false branch are a scope. So after the conditional x doesn't exist anymore. Scoping, yes. Okay, let's do something something useful with lambdas. So square brackets, type stuff, recipe, that is a lambda expression, and you can assign it to a variable. And now that variable acts like it's the function described there, and you apply it to a couple of arguments. So instead of defining a function, you make a variable that is a lambda expression. Yeah, why does it say auto? That is because the lambda expression has a complicated type. And in fact, it's not just a complicated type, it's a type that is dynamically generated. We'll get to that in a second. Right, so assign a lambda expression to a variable and then use it as a traditional function. Okay, I want to do this in class, and that'll give you a couple of minutes to take a break from having to pay attention. Newton's method. I assume everyone knows what Newton's method is. It's a method for finding the zeros of a function. So you have a point xn, and then you evaluate the function value, the derivative, and in a couple of steps, you find the place where the function crosses the x-axis, the 0. Why am I telling you this? In very old computers, there was no hardware for square roots. And so how would you do a square root? Well, you do it iteratively with Newton's method. You say the square root of 2, that is the place where x squared minus 2 is 0. And so you do the Newton's method, and if you write out the formula for Newton's method, then you see that you can do square roots if you can do divisions. So if you have divide hardware, you don't need square root hardware. Yay. I once actually used this to implement square roots in tech, if you can believe it. Anyway, so if you go to the repository for the book, and the repository is, let's see. Did I give that? Didn't I? Okay, I need to, it's almost the link that is in Slack. Oh, it's actually the link. Yeah, go to the link that says textbook download, and that has the link to the repository. So I hope you did that last week for your exercises. So make a git clone. There is a skeletons directory, and that's where you find the file newton.cxx. And that gives you a code for computing Newton, and rewrite this using lambda functions. Okay, 5 minutes, 5-minute break. We'll do this exercise, and then there is another one coming up. So you get another 5 minutes there. Okay, 5-minute break to do this. If you're stuck, questions in Slack. You can probably let it roll and edit it out later. Okay. Yeah. Did everyone solve this? So instead of having the two functions here, you would do auto F is capture something. And I'll bet that the compiler is able to deduce the return type. And your calling code stays the same. You could probably also do stuff. Did anyone solve it a different way? Let's see, where am I? GCC, Newton. What? That is supposed to work. Am I including something? Okay. I'm not sure what's happening here. Oh, ha. Yay, the obvious things. Okay, if someone knows how to get rid of this Mac OS warning, then I'd appreciate hearing it. Thanks, David. Ha. And then right. Why do we use Newton instead of something simple like a bisection? Does anyone remember their numerical analysis classes? Quadratic convergence, yes. So 0.25, so that's 1 0 and then 2 zeros and then 6 and then 12 zeros. So the number of digits correct doubles every time. Yeah. Okay. So this way you use somewhat pointlessly the lambda expressions. Okay, so let's say you have a scenario. Absolutely. You have the scenario where you have a function and you have a function apply to 5. It takes a function as input and it returns that function applied to 5. Okay, in C you don't too often pass function pointers, but it does occur. For instance, in a numerical library where you so that's what we're going for. You have a Newton routine, it takes a function and then it returns the 0 of that function. Okay, so we're going to work on the case where the function becomes an argument to another function. Okay, in C, you would write it like that. You had that strange void star F. I always have the hardest time remembering where all the parentheses go, but yeah, on line 2, I'm passing a function with int in, void out into the other function apply to 5. If you do that with lambdas, so you on line 5 and 6, you say apply to 5 lambda, because that lambda expression is just a function. Then you run into the problem that the type of a lambda expression is automatically dynamically generated, and so you don't know how to define your apply to 5 function because you cannot write that type. So that's why we need something else, include functional and using standard function. And then you can say, and now we're doing the Newton thing. So the function Newton root takes 2 functions, namely f and f prime, and to make it possible to pass lambdas into that, you say it's a function of double out, double in. And you need 2 of those. So this function thingamy is some deep template magic, and that makes it possible to pass lambdas into the function Newton root. Okay, another 5 minutes break where you get to figure out how to write the Newton root function. So go to your terminal, take all of this, let's see, double Newton root, and figure this one out for yourself. Okay, you get 5 minutes to do this. So I've already given you the functional and function, and by looking at the slides, you can sort of crib this. So it's a Newton is a function of, we're doing everything in double, so double, double and double, and that is F, function of double F prime. And then here you call Newton root. Let's immediately see out it. Newton root of F and F prime. And it does the same thing again. And just to show that lambda expressions offer you some compactness. You don't actually need to assign them to anything. You can completely write it in place. Okay, so if you need a function only for a very temporary purpose, then you can write the function recipe in place as a lambda expression. No questions? Captures. So far, I've let the square brackets be empty. What can you do with those square brackets? Well, you can make a function that dynamically depends on its context. So it's called a capture because it captures the environment and bakes it into the function. So for instance, in the little code example that I'm showing there, I have a variable exponent is 5, and now I make a function power 5. So it becomes a function that takes an x as input and then returns x to the power 5. And I do that by capturing the exponent variable. So it copies the current value of exponent and it copies it into the function. So power 5 is now completely a function of one argument with the variable exponent copied from the environment into the function. And there's all sorts of variants of how you can capture things. You can capture multiple variables by spelling them out. You can capture everything known at that point by using equals. Yep, I'm not showing that. Let's see. So this Newton function, there is a 2 in the F and a 2 in the F prime. Those are not the same 2, right? The first 2 is what you are computing the root of, and the 2 in the F prime is the derivative from the x squared. So they're not the same 2. Okay, see if you can figure this one out. So let's say double number Cin into number. So now how are you going to compute the Newton root of that number? Does anyone want to suggest, type a line in Slack, use back quotes or triple back quotes? Can someone suggest how you would how would you solve this? So the problem is that without lambdas, you would write you only have to redefine the definition of f, not of f prime. So to do the square root of n, you would have a function f that would be x squared minus n, and that computes the square root of n. So traditionally, you would write a function square root minus n that takes an x and an n. But the Newton method only takes a function of one real. Here, you cannot tinker with the fact that Newton takes a function of one variable. So you cannot have a function of two variables. Okay, I'm not getting any suggestions. So you would do that by capturing the number and then using that. Guess we use a capture, yep. So you capture the number of which you want to compute the square root, bake that into the function, and then now you have, now f is a function of one parameter, but with the capture, it now computes the quadratic function that you wanted. Okay, that's it about captures. You can do this one at home. It's a cute one. You don't actually need derivatives, right? You can compute that as a finite difference. So can you write a Newton root that takes only a function f? Can you write a Newton root that how do I say this without giving away the clue? Can you make it so that you could call Newton root both with f and f prime or only f? What's the magic word? Let's see. The magic word is polymorphism. So you can have a function defined two different ways as long as, for instance, a number of arguments is different. Okay, capture. So normally capture is by value, but you can also capture by reference. So here you see ampersand count. So now you're capturing a variable from the environment, but you capture it by reference. So if your lambda expression changes that variable, then it's also being changed in the calling environment. So count if f is a function that, assuming that there is a function f, you give it an argument, and if the argument, if f on that argument is true, then you increase the count by 1. So this is useful if you want to go through an array and count how many elements satisfy a certain condition, right? The for loops like that. Actually, you don't code it out like this. There is a section on algorithms that we will get to in a minute. Let's see. Yeah. Okay, so this sort of stuff, counting how many elements satisfy something, that is already done for you in the standard library. So there are routines like for each and transform. And so you apply them to an array, you apply a function to an array. So for each applies a function to each element. And so you can do things like counting them. Transform takes an array and is able to transform the elements into something. We'll get into more detail, but I'm just mentioning that these that if you read about C++ and someone says algorithms, then this is what they refer to, the algorithm header that has these routines. Okay, we do a topic that I find kind of elegant and interesting. Union-like things. So, yeah, I could give this a subtitle. If it ain't one type, it's another. So what if you're dealing with multiple types at the same time? So last week when I was discussing functions, I gave an example of, was it actually this example? Compute the square root, or say that you couldn't compute it because it was negative. So this is going to be the running example. If a number is positive, say this is the square root. If it's negative, say I could not compute the square root. So you can write this in plain C. You write a function that passes a number by reference, and so you square root it. Or the function returns a Boolean and says this number was negative. And then you use that for a couple of x values. You say if root or error is true, then the root is, otherwise you say could not take the root. This is the C way of programming, and I'm going to show you a couple of different ways of saying it in C++. For instance, if I mentioned functional style programming. So some people think that it's a very clean way of programming to have the function arguments always only be in and only return results through the return type. Okay, how would you deal with a return type that can be either a Boolean or a float? Well, you could, for instance, make a struct that contains a Boolean and a float. Or in C++, make a tuple. So, yeah, this notation is a little unwieldy on lines 6 and 8. If the number is negative, then you make a tuple of a bool float consisting of false and -1. If the number is 0 or more, then you make a tuple of bool and float, namely true and square root, and then you somehow catch that tuple and you say, okay, if the first member is true, then the second member is the result. This is not the best way of doing it, but it illustrates the point that you can make a tuple of multiple different types. And so you can deal with these scenarios where you need more than one type in a return result. To continue on tuples, you can write your function a little more compact than this. So in the left panel, if the return type is returned as make a tuple of a bool and a float, then the compiler, and it does that both times, and the compiler can figure out, okay, no matter how I'm coming out of this function, the return is a tuple of a bool and a float. And so you can do what's called auto return type deduction and define the function with auto. What I find the most interesting way is that you specify the return type explicitly as tuple of bool and float, But now that the compiler knows that that is it, you make the return statements with curly brackets and very elegantly say, okay, make your tuple bool float out of false -1 or true and square root x. So the second one is a very elegant way of writing it, and it's almost as good as Python, right? In Python, you can say return x comma y, where x and y are of completely different types. By the way, I'm using tuple here, which works for any number of components. If you return just two entities, then you can use pair instead of tuple. Okay, so now I've only showed you the function that returns a tuple. How do you use that function? In Python, you can say a comma b equals that function that returned x comma y. In C++, you can actually do the same thing. I think this is C++ 17. So line 1. So you have your function maybe root, which returns a tuple of bool and float. And now you say auto square brackets, something Boolean, something floating, is that. And so this is like a double variable declaration with two completely different types. This is a very elegant way of dealing with things, and it's known as structured binding. I'm not sure what the structure and what the binding is, but that's how it's known. And this is a great way of dealing with pairs and tuples. Over the past week, I've been coding a cellular automaton and two-dimensional cellular automaton, and the sweep over the whole thing needs to be done in a random way. And my code actually looks like 4 I comma j in function call that gives me permuted indices. So yeah, there are legitimate reasons for applications for these structured bindings. Okay, so that's how to deal with tuples. Very elegant. Before C++ 14 or 17, it was nowhere near as elegant. You didn't have the auto type deduction, and you had to take your tuple apart by saying get the 0 or get the 1 component. So if you come across this, it is someone who hasn't heard of the latest C++ 17 techniques. You write it like this, much better. Okay, so like I said, doing square root or report that it's not that it couldn't be done. It's not the most elegant way of doing it. What you actually want to do is optional. An optional says it's this value or it's not. So number or an error can be done with a so-called optional. So maybe root returns an optional float, it means you return a float value or you return no such float. So if line 3, if you return curly brackets, it means you returned optional false or optional no such float. And now if you do your root calculation, note that in my if statement, I use an initializer part, right? So I first initialize a variable and then I test it. I hope you remember that from last week. So root is maybe root of x. So root is an optional float. And now I can test if root has a value, then I get the value. And otherwise I print something or I ignore it, whatever. Okay, so optional is really cool. It's to deal with this case where you want to return that computation could not proceed. Optional comes out of the optional header, and you do using standard optional. You declare your function as optional whatever. You return your whatever object, or you return curly brackets. Let's see. Yeah, if you try to get the value of something that doesn't have a value, then I should leave out this slide. Now, with optional, you can only say this is the value or no such value. If you want to say this is the value or no such value for this reason, for that reason, for that reason, then C++23 has something called expected. So you expect to be able to compute the square root, but you may want to say why you couldn't compute it. Okay, so you now your square root function returns an expected double, and if something unexpected happens, then you return a string. And so, for instance, this routine says I couldn't compute the square root because negative. I couldn't compute the square root because it would underflow. Okay, and now you compute this, you get the value, and you can test the number by itself and get the value, and otherwise there is an error that gives you the string that okay, so what have I shown you? All sorts of ways of returning multiple types or an alternative between types. So there was the tuple, if you really need to return multiple things. There was optional. Which is something, or say that it couldn't be done. Expected, which goes into more detail of why it couldn't be done. And then there is the variant, which is really return this type or that type. What is a variant? Yeah, it's this type or that one, and then you can test which type it is. So, for instance, if you have a variant of an int and a double and a string, then now there is a function index. So if index is 0, then your variant is an int. If index is 1, it's a double. If it's 2, it's a string. And so there's usually different ways of getting at the value. Here I'm using star to look up. So in the previous slides with optional, I used the dot value method. I need to look up if that works here too. Usually the two are equivalent. So multiple different ways of getting the value. Okay. You get 2 minutes to, or you get 1 minute. So Laura, let it run. You get 1 minute to post your answer in Slack. So suppose you want to compute the roots of a quadratic equation. So discriminant negative, there are no roots. Discriminant 0, there is 1 root. Discriminant positive, there are 2 roots. Okay, now this function compute roots, what would its return type be? I give you a minute to post your guess in Slack. Here, take a look at the table of contents to see what your options are. No one? Okay, so first of all, you want to be able to say couldn't take a square root, so it's an optional. And if you can compute, sorry, not square root, the roots of the quadratic function, so it's an optional, because if false, then you couldn't compute roots. And then there's the case of one root and another. So it's an optional variant double pair double double. Okay, optional of variant, and it's a variant between single root double, multiple roots, pair of double double. Okay. Last major topic for today, before I do a whole bunch of small ones, is iterator mechanisms. Those have evolved. I guess they were always part of C++ because it's a very basic mechanism. So it's how you iterate through an object. You can iterate through a vector, get its elements. I didn't show you what a map is. A map is an associative array. So for instance, use a string as indexing to get arbitrary objects. And so you can iterate through a map, you can iterate through a set, you can iterate through all sorts of things. And the mechanism for that has always existed. In C++ 11, iterating was made more elegant by having the colon range notation. And then in C++ 20, the whole range concept was turned into a first-class object. Some ranges now actually exist in the language as opposed to just being a concept in your head. Okay, iterators. If you have a vector, so far we've only looked at getting values. So you can index them with square brackets or the add method. I mentioned that there is the front method for get the first element and the back method for get the last element. But there is something called begin and end. And begin is like a pointer to the first element, and end is like a pointer one beyond the last element. C and C++ use this indexing with a non-inclusive upper bound. So you have a vector, and then you declare a variable pointer to be the begin of V. That is not the first value, it's a pointer to the first value. Well, it's not a pointer, it's an iterator, but it's conceptually, it's something pointerish. And so you can indeed use the star to dereference it. And that tells you what the value of the first element is. And then you can increment it, and etc., etc. Note that on line 9, the end method gives you a pointer beyond the array. So if you dereference it, you may get a segmentation violation. You may just get a nonsensical value. But if you minus the end, you wind up on the last element. Okay, begin and end. And as you can see on line 5 and 12, you can do arithmetic on iterators. So you can increment them, decrement them, and it's like a pointer moving through your array. You can do all sorts of fun things with iterators. For instance, because arrays are dynamic, you can erase elements, you can insert elements. Let's see, I have a vector, it contains 1, 2, 3, 4, 5, 6. Oh, and where here on line 2, I said my begin thingamy is assigned to an auto variable. Here I spell it out. the type of begin is vector of int iterator. So that syntax may look a little strange, but it's the vector type and then the subtype iterator of that vector. So vector int iterator is a type name. Okay, and so second is begin and one place to the right. So it points at the 2. The element fourth points at 2 plus 2, so it points at 4. And now in line 4, I say erase from 2 to 4, and it's a non-inclusive upper bound, so it will erase the 2 and the 3. And now if I print the first 2 elements of the array, so 2 and 3 were erased, and I get 1 and 4. Okay, so iterators are useful for all sorts of array manipulation routines, like erase and here, as an example, insert. Do bear in mind that the upper iterator is always non-inclusive. Yeah, arithmetic. Okay, so here you've done array manipulation. There is a bunch of algorithms that you can do with iterators, and by algorithms I mean in a very strict C++ technical sense, things like what I've already mentioned, for each or transform, filter, in this example, accumulate. So you have an array of things, and from a begin to a certain endpoint, you want to sum or product or max whatever the values. Okay. Include numeric using standard accumulate. I have a vector. I take my begin and my end iterator, and then I say, okay, accumulate from first to last with a starting value of 0. And if I don't supply an operator, then it's a sum reduction. There are a bunch of reduction operators predefined. So in this example, I have a vector and I do a product reduction. So multiplies, probably also comes out of the numeric header. It is sometimes a little confusing what header stuff comes from, so I usually have to look it up. Anyway, product reduction. You can write your own reduction operator. Yeah, if you write your own reduction operator, see the right panel. I'm using a lambda function, of course, a lambda expression, because the reduction operator is something really simple. And so why would I have to define a whole new function? I have to think about the name. I just put the recipe in place. So this combination of C++ algorithms and lambdas is very, very common. Your accumulate function is basically a fancy plus, and it is literally 10 characters, 12. And so you just write it in place as a lambda expression. So what we've done here is iterating over things like vectors, and where was that thing? Line 2, the vector class has a built-in iterator concept. So a vector knows how to iterate. What if you write your own class that is something vector-ish and you want to iterate over your class? How do you do that? You can write your own iterators. And This sort of thing in C++ is elegant and it's very powerful because you introduce new abstraction levels by which it becomes very easy to abstract concepts away. You don't have to spell out, take these components, add this operation to it. No, you say, apply some named operator to the whole of your object, or not even named, lambda. Okay, so just like range, so realize that range-based iteration for all element in vector, do something with element, is a whole lot of syntactic sugar introduced in C++11 around the basic iterator concept. So it is exactly the same as saying my vector of int iterator, something starts at begin, and until it reaches the end, you plus it, and then somewhat inelegantly, you get the value by star dereferencing it. Okay, it's not a dereference, it's a unary operator, but it looks like a dereference of a pointer, right? But it's not. Okay, yeah, syntactic sugar that makes life a whole lot easier. But from this example, you see that if you want to write your own ranging concept, then you need a subclass iterator, you need a begin function, you need an end function, you need a plus operator, and you need a dereference operator. Okay, so how do you do that for your own class? Yeah, that's basically what I said. Okay, so let's say I have my own vector class, and here you have a traditional C int star array because I'm malloc-ing it myself. Yeah, if you're careful enough, then you can make your own objects and you can still malloc stuff, but keep it away from the users of your class. Okay, so I make my own vector, I manage my own storage, and but the essential part is that inside my new vector class, I have an iterator class, and my new vector has a begin method that gives me an iterator, and it has an end method that gives me an iterator. And so all of this is on my way to being able to say, I have my own new vector, and now for everything in my new vector, do something with it. Okay, so you start out by writing the begin and the end operator and having an iterator class. Yeah, it kind of depends on the context, but so you need to be able to write a plus operator, a star operator. You probably need both an equals and a not equals operator to test for the endpoint. And in the training that I didn't wind up giving 2 weeks ago, I was illustrating this with OpenMP. Okay, I don't think I will go into this in detail. But basically, it is possible to write your own iterator, and this is a very powerful mechanism. So you can make your own complicated objects with your own storage management and still be able to use this range-based notation. This range-based notation, there's nothing magic about it. It translates to an iterator interpretation that uses the begin, the end, the plus, the deref. Okay, so you can write your own iterators. Very powerful. In C++20, this whole stuff was extended even further. ranges. So in C++ 11 or so, you can have a vector and then say sort it from begin to end. So you need it to begin and the end. And you can make mistakes there. You could, if you would say sort it from the begin of this vector to the end of another vector, then yeah, I have no idea. Your code would run forever and then bomb with a memory error or something. So why can't you just say, okay, here's my vector, sort it, and don't have to spell out from beginning to end. And so the ranges library has variants of a whole bunch of routines where you can just say, okay, sort, and this is the container. Okay, now what if you want to sort, but leave the first and last element in place? Okay, how are you going to do that? Well, that is also part of the ranges library, and that goes like this. So you can take a vector and apply various transformations to it. So for instance, this slide is a little busy. On line 1, I have a vector and I print it out. And now on line 4, 5, 6, you see the vertical bar, in Unix, a pipe. It does the same thing in C++. So you can have a vector, consider it as a stream of things, and then pipe it into some filter-ish, transform-ish thingamy. So you have your vector v. Okay, I cannot select that. So v gets piped into a transformer, which turns it into a different vector, and then it gets turned into a filter, which picks out certain elements. And then in line 11, I turn that whole thing again into a vector. Why do I do that? Okay, so so I have my original vector, but transform and filter are so-called views. So a transform does not create a new vector. It creates something iteratable. So if you can pluck elements out of it, but it's not an actual object. It's something that can yield values. So it's a little getting used to the fact that you have actual iteratable objects and views, which are the term lazy evaluation is used. The thing is not constructed, but you can successively ask for elements out of it. And that's where the pipe notation is used. And that's all I'm going to say about it. So you can do a whole bunch of things with this. If I teach this again next year, I'll probably devote more time to it. But yeah, so note that at no point am I explicitly iterating. I'm definitely not indexing through my vector. I'm not even iterating elements over my vector. I say, okay, here's the whole iteratable object, and now pipe that through a transformer, meaning transform every element, and that again gives me a whole iteratable thing. And then I say, okay, filter, but at no point am I using the index, or am I looking at individual elements. Transform and filter, take the whole thing and then apply this lambda expression to each element. Okay, very nice abstraction mechanism. C++ 20. For as far as I know, most compilers support this pretty well. Okay, namespaces. I don't see, yeah, if you start writing libraries, then that's a useful thing to know. Templates. What are templates about? No, not going into that. I find that in scientific codes, templates don't have a whole lot of use, but you've seen vector of int, vector of float. Okay, the int and the float is like a function parameter, but it's now a parameter on the type. And so it's a parameter. So vector is a templated type because it's a vector of another type. And that mechanism is called templates. In scientific codes, I don't see too much use for it, so I'm not going to go into it. Oh, let's do something about exceptions. So exceptions are C++'s way of handling runtime conditions. So if something really unexpected happens, if you want to write to a file, but you couldn't open the file, then you need to handle that as an exceptional case, and hence the word exception. So you say throw, and you can throw anything. You can throw an integer as a result code. You can throw a string as a diagnostic code. You can throw whole complicated objects that describe God knows what. So if you do throw, then your routine is aborted with a certain exception. And now somewhere up the calling tree, you can then say, okay, at this point, I'm going to catch exceptions. So you have a routine, do something which you know is able to generate exceptions, and then you catch it. So for instance, if the do something routine can throw an integer, then you can say, okay, catch the integer, and if you catch that, then apparently some error happened, and you can do something with that. Okay, so throw, catch is the mechanism for dealing with error codes in C++. You can handle, you can throw many things, and so you can catch all of them, or you can catch something by default. You can make exception classes. Yeah, all sorts of things you can say about exception, but basically throw and catch, that's basically it. And of course, C++ being what it is, if you leave a routine through a throw case, it will deallocate all the objects in all the intermediate routines. So memory management is completely taken care of. So this is a very clean way of abandoning a routine. I've mentioned the keyword auto in a number of places. So you can use it in an obvious case. If you have a very complicated type, a vector of pointers to whatever class, and then a reference to that, you'd have to spell it out twice. Type variable is constructor. So you can leave it up to the compiler. If this is what I'm creating, then that's the type of the variable. So you can use auto there. Auto type deduction, this was C++ 17, I think. If it's clear to the compiler what the return type of a function is, then just say auto and the compiler will figure it out. The same thing happens in class methods. But line 5 and 6, something you need to note the reference. So functions can return a reference, and the the auto that you use here sort of doesn't see the reference. Yeah, my function access returns a reference to the internal data, but now if you use that function in a calling environment and you only say auto, then the fact that it returned a reference is ignored, and so this is actually by copy, and you need to insert the reference. So auto reference is whatever, is a common idiom. Let's see. So that's all I'm going to say about auto. More things about C that you should no longer use. Don't use old style parentheses casts. There is, yeah, so the C cast is look at a byte and now pretend it's something else. That is very dangerous. And in particular with C++ classes, it's very dangerous because if you inherit, then the starting byte of one class is not necessarily the starting byte of derived classes, etc. So static cast, dynamic cast, const cast, reinterpret cast. So don't use the parentheses cast, read up on what the proper cast is. That's all I'm going to say. Something about const. I think I'm going to take a 10-minute break. I've been talking for long enough, need to get some water. So 10 minutes and then I'm finishing off a bunch of small topics. Yep, very good. Okay, there's a whole bunch of minor topics that I want to get out of the way. Const. Yeah, last week you saw the const ref idiom in a number of places. So declaring things const is a way of telling the compiler that certain things are invariant or constant in your code, and so the compiler will tell you if you are violating that contract. So this gets you on your way to functional style programming. If a parameter is only input to a function and it should never change, then declare it as const. If a function is functional, yeah, side effect free, and a function only has effect through the return type, then you can declare a function to be const. And then the compiler will also complain if you are changing things that you shouldn't. So it's a way of preventing a number of potential runtime errors. So a lot of the safety that supposedly you get out of the new Rust language, you can get out of C++ if you make everything const that should be const. Rust is like C++ with const as default and mutable as something you need to explicitly indicate. In fact, some people are experimenting with making a language on top of C++ that does have the defaults correctly, or whatever correctly means. Anyway, const is a way of making your program safe. It is not for optimization. So I don't think the compiler does things like constant expression elimination or lifting things out of loops because they're constant. There's too many ways you can get around that. So it's for code safety, not for optimization. So first of all, constant arguments. If you pass an argument by value, then the calling environment value gets copied in, and after that it acts like a local variable. Maybe you want that local variable to be unchangeable, so you can declare it const. More useful is passed by const ref. So arguments are by default copied, and if you pass a large array into a function, it makes a complete copy of the whole array. You don't want that, so you pass it by const reference, meaning a reference to the array is passed, and then you declare it const to prevent the array from being inadvertently changed. But inadvertently changing, I'm sure you know your own code. Yeah, but what if you pass it to a library routine and you don't know if the library routine maybe decides to tinker with the argument? Okay, so const. Side effects. What are side effects? Side effects is anything that a function changes that lives outside of it other than through a return type. So in this little bit of code, the get method, because it only returns a value, obviously it doesn't change anything outside the function, and so you can declare that one const. The inc method increases something internal to the object, but outside of the function, and so that function has a side effect. If you would declare that one const, then the compiler would say, okay, doesn't make sense. On the other hand, the function add_to, which makes a change through the parameter, is const because it doesn't have a side effect. Okay, earlier I think I said that const, if the only changes through the return type, should be return type and arguments. Okay. So this routine is a bit much. Take a look at line 7 and line 10. So line 7, this object has an add method that gives a reference to something inside the object. So that means that if you call that method from the calling environment, then you get writable access to the internals. Now, line 10 is also auto ref add, but that one, both the result reference and the function have been marked const. So you get access to the internals by reference, which for instance saves you on copying, but also you've marked the function as constant, meaning this function cannot change any of the data members of the object. So this is a very tricky case. You have an add function that is polymorphic. In both cases, it returns a reference, but one is marked as this can alter, this can have side effects, and the other one is marked as this will not have side effects. And the compiler can actually deal with this. So yeah, this is an idiom that you can come across, that you have two different, that you have read and write access directly to internals. C++23 is going to make this a little more elegant because basically I have the same code in two places with only a different function header. C++23 makes this a little more elegant. It's called deducing this. Yeah. Oh, okay. In the C++ community, there's a lot of noise about const expr and const eval, which means that if code can already be computed by the compiler, it's no longer done at runtime. And there's various uses for this, and I've never had a use for this, so I'm just mentioning it to you. Yeah. If you define a recursive a factorial routine and you call it with a constant, then the compiler can actually already compute that. So yeah, I'm not impressed, but maybe you have a use for it. Okay, and that is it for const. Okay, here come a slew of something gone wrong with the table of contents. Here come a slew of standard library topics. Complex numbers exist in C++, so you can have complex float and complex double, and you get the real imaginary part. You can do arithmetic on them. Yay, you don't have to spell it out anymore, and there is a literal I for the imaginary number. Yeah, complex numbers. C had a limits.h file that contained the location where you have overflow, underflow, and all that. It's more sophisticated in C++, so it's numeric limits, and so you can now say, okay, of my limits for a long integer, what is the max? There's a whole bunch of things. There is the min, the max. There is for floats, there is the denormal min. So yeah, there's a whole bunch of things that you can ask, but it's nice and elegant that it's now library functions rather than just a header with constants. Right, there's max, there is denorm, min. Oh, you're right. What is min? Is that closest to 0 or is that most negative? So min is smallest positive. Lowest means most negative. Oh, right. And there is a epsilon routine. So in fact, machine precision is now interrogatable. More things of C that have been replaced by something more powerful and more elegant, random numbers. So please don't use rand and srand. Those come with no guarantee on the quality of the random number generator. And if you need an integer between 0 and 100, I see people write rand modulo 100. That is indeed a number between 0 and 100, but especially for random number generators with a small period, this is biased away from the highest numbers. So yeah, there's various conceptual problems with the way the C random number generator is used and is designed. So C++ has its own random class. You need a random engine, which is something that drives your random. And so it's not a number by itself. You need to take this engine and then feed it through a Poisson distribution, whatever distribution. So this is more abstract, and you can initialize this with a random device. So that's like setting a random seed. Okay, you have your random engine, and then you make a distribution. So for instance, uniform real between 0 and 1. And then you say, okay, this distribution applied to my generator. It's not the generator applied to the distribution. Maybe a little counterintuitive that it's the way the arguments are passed, but you say distribution based on a random number generator gives you a uniform real. And likewise, there is a uniform int distribution. So a roll of the dice is an int distribution 1, 6, where now the bounds are inclusive. Time measurement. Okay, so this was random. Time measurement comes from a new library, Chrono. So no tinkering with get R usage and time of day and whatever system mechanisms. So there is Chrono, which is a little complicated to use, but it has all sorts of nifty features. So you can have different clocks. And you can ask your clock what precision it is, probably. And then you have your clock and you ask the clock, okay, what is now? And now is a time. And time is a time object. You can convert that to something, but mostly what you use is duration. If you subtract 2 times from each other, you get a duration. And now you can cast your duration to seconds, microseconds, nanoseconds. And that is still an abstract object, and then you can count it. So Chrono, again, I can say more about this, but I'm just mentioning that it exists. Chrono is only for time durations. Absolute time, as in time and date, turned out to be rather complicated to standardize, and so that is C++ 20 or 23. Anyway, I've never used it yet. I think Chrono is, I don't know how old Chrono is. Okay. Yeah. A couple more things that you may have used Python for. Directory tree walkers. So the file system library was part of C++ 17, and I have not been able to test it yet because Intel refuses to implement it correctly, or they consider it low priority or something. Anyway, our Intel compilers do not properly support this. Regular expressions. Oh, it's supposed to have an output here. Sorry, slide is broken. Yeah, this seems to be a somewhat inefficient implementation. People gripe about it, but if it's not a performance critical part of your code, then hey, regular expressions, it works. It's fairly easy to use. One of the big things in C++ 20 is modules. So yeah, 30 years after Fortran 90, C++ is catching up with the notion of having modules. Except that none of the compilers really support it in all defined aspects. So basically, I'm not telling you this because I don't have a compiler that allows me to do so. But modules is going to be a replacement for the whole header mechanism. So so you define a module, and then you export names from that module, and then in another module you say, okay, from that module import the following names. And that's a lot better than the header files, which rely on all sorts of textual trickery. Anyway, but this is the main topic in C++20 that is not yet majorly available even in 23. Let's see. Unit testing. Yeah. Does anyone here in the audience regularly unit test their programs? I'm working on something major with lots of intricacies, and yes, I write unit tests hand in hand with writing my library. So, all right, Edsger Dijkstra, my hero. Today, a usual technique is to make a program and then to test it. But program testing can be a very effective way to show the presence of bugs. It is hopelessly inadequate for showing their absence. This is from his, what's the ACM, the Turing Award lecture. Yeah, so Dijkstra didn't believe in testing. Still, testing is a good way of increasing the confidence in the correctness of your program. So testing, unit testing is that every part of your program should be testable. And so you, for every bit that has a clearly identified function, you write some tests and you test. In this case, I get the right result. In this case, the test fails. Unit testing, test-driven development. Okay, what I want to mention is that there is a great library, Catch2, open source, been using it for many years. I'm happy with it. It's easy to use, and so you make your test cases, and you can select to run all cases or only certain cases, and then you say require, so it computes a line, and then it tests that some expression is correct. Yeah, I'm not going to say much more about it. Require, require throws, require no throws, so that's exceptions, etc. I'm just mentioning Catch2 is a very commonly accepted unit testing framework. It's one that I would recommend. And I believe that is about it. So yeah, I'm mentioning at all sorts of places, C++ standards. So there is unfortunately still old code around that uses C-like programming techniques that you shouldn't use, and some codes don't use modern C++ techniques. So C++ 98 and 03, yeah, they were necessary stations on the way to where we are now. 11 is the start of modern C++, so range-based loops, lambdas, smart pointers, all the big topics that I've been going over today and last week are basically in C++ 11. 14 extended these mechanisms and fixed a number of things. 17, some of the things that I discussed today, so optional, structured bindings, init statements. Init statement I actually did last week, come from 17. 20 did a whole bunch of things. Modules, unfortunately, not terribly available. Coroutines, it's a form of parallelism, and I guess in the web server world, people love it, but I see no use for it. Talk to me about parallelism. I'll tell you about OpenMP and MPI, both of which can be very elegantly used from C++. Yeah, whole bunch more things in C++. 20, oh, ranges. I touched on that today. So increasingly abstract and more elegant ways of dealing with iteratable objects. So don't write loops, use ranges. 23, the only thing I'm going to mention is MD-span. So I touched on that last week, I think. Vectors own their data. So you cannot have a vector and then have a subvector of that thing. If you try to create a subvector, then it will allocate new space and copy the elements over. So in C++, vectors, you cannot do what you could do with C pointers. You have a pointer to your big array and then a pointer to a sub-array of it. Two-dimensional array, here's the top left corner, and here's the location of a sub-array, right? Anyone that's done LAPACK programming knows the why you have an LDA parameter. Okay, so that was not possible in C++. Then in 17 or 20, they added span, which made it possible to have something that looked like a vector, but it didn't own its data. So it could be a sub-object of another vector. C++ 23 is going to make that even better by having a multidimensional span. So finally, you get something looking like Fortran 90 array notation. Okay. And that's all I have. Yep, the very last slide. Okay, so yeah, download the latest version of my slides and study the code examples. What did we do? Last week, we started with object-oriented programming and the functions chapter about parameter passing. Definitely, absolutely have to know that. Object-oriented programming, how to make a class objects and all that. Vectors, so don't allocate arrays, don't use new in case you know about that. Just use standard vector. Standard array if you have one of the size that is known at compile time. So C++ containers are way better than C mallocable stuff. Strings, you can plus them. I/O, elegant mechanism that unifies screen and other output. Smart pointers, no more memory leaks. Lambdas, pass small functions into algorithms. Union-like things, so variant, optional. Certain things can be very elegantly expressed that way. Iterators. Okay, no more indexing by I and J unless you need to know the I and J. Iterators can simplify that stuff, and you can write your own iterators over your own classes. I didn't say much about namespaces, templates. Exceptions are error handling, auto-const. I hope you've seen enough examples that you sort of have an idea what happens there. Someone posting in Slack. Memory alignment through STL vector. Good one. You can write your own allocator. That's a topic that I still need to dig into. It is possible to guarantee that. Good question. Where was I? Auto casts, don't use the parenthesis stuff. Auto const, and then yeah, new random library, time measurement, all very powerful, cool stuff. And still coming up modules, and I mentioned the Catch 2 unit testing framework. Okay, that's it. whole lot of material. I hope at least some of it sticks in the sense that you've now seen that it exists, and you can download my textbook from the same link that you have, which is 600 pages of, I hope, reasonably verbose explanation. Okay, that's it. We're 15 minutes early, but I'm sure you've had enough of my voice by now.